Okay, we're going to move on to example H now. We need to graph and simplify. You'll see where I'm going with this in a minute, why I said and simplify. So you see that we've got an OR situation. Well, that's a lot easier to handle. We just need to graph directly onto the number line, and we'll keep the sum of the regions. So let's graph the endpoints, 1 and 3. And now we'll graph directly onto the number line. First, x is less than 1. Or, so we can just add it to the number line, the sum of regions, x is less than or equal to 3. Now look at this. As we do the second condition, it actually shades right over what was previously an open circle. So there's our graph. So what do I mean by simplify? If you look at the graph, it's quite clear that our final solution is x is less than or equal to 3. It turns out that this first condition was superfluous or extraneous. It wasn't really required in order for us to get our solutions. What we're saying that is if x is less than 1 or it is less than or equal to 3, that means that any value less than or equal to 3 is going to meet at least one of these two conditions. Let's do part I. Now we've got an AND situation, so I'm going to graph above the number line each independent inequality, and then I'll look for the region of overlap. So we'll start with -1 greater than or equal to -1, and x is greater than 2. Oops. Darn, let's undo that, sorry. Above the number line, so we're at 2, strictly greater than. Alright, where is the region of overlap? There's no overlap yet. Starting right here, there's an overlap, although not quite at 2. Everything bigger than 2, I can see that both of my inequalities are represented. So the region of overlap, I can simplify this by looking at my final graph and say, oh well, I'm simply dealing then with x greater than 2. This condition then, this first one, ends up being unimportant. If you know that x must be greater than or equal to -1, and at the same time it must be greater than 2, well, clearly we're only dealing with the values that are greater than 2, because here we need both of the conditions to be met, and this is the more restrictive condition. Let's go down to part J. Alright, now we need to graph and simplify. Oh good, it's an OR situation. The OR situations are easy. We just graph them directly onto the number line. So we've got endpoints at -3 and at +2. First of all, x is less than 2, open circle, and everything in this direction, including the arrow. Or x is greater than -3. Now I guess I would have an open circle here, but I've already shaded right through it with the OR. And I need to shade everything to the right side, which includes going through that previously open circle at +2. And I need to shade in the arrow. And let's look at the final result. Wow! I've shaded in the entire number line. And thus, if I'm going to simplify this situation, I can see that x is all reals. The entire number line, the whole real number line has been shaded. X is all reals. Part K. We got an AND situation. That means that we need to graph above the number line and then look for the region of overlap. So we've got 0 and we've got 1. Let's first graph x is less than or equal to 0. Here it is. Now let's graph x is greater than or equal to +1. Here it is. Now let's look for the region of overlap. Are you seeing what I'm seeing? There is no overlap. These two inequalities don't occur simultaneously anywhere. And so on our final number line, we don't shade anything. We'll leave it completely blank, and our simplification is, I mean to say that x has no solutions. Okay? Now it's possible to express these solution sets in two different notations. We've already looked at one of the notations called set notation, where we're using inequalities. But in fact, that's a rather informal way of expressing set notation. There's a better way of expressing set notation known as set builder notation. And I'll show you that in a minute. We also have interval notation. So those are the two notations. Set notation, which we could do it more formally than we've been doing in a way called formal set builder, and the other notation is called interval notation. All right, let's look at each of these in turn. Formal set builder notation will include these curly braces, or you can see these funny brackets, and the number set to which the solutions belong. I'll get to one of those examples in a minute. Interval notation describes the endpoints of the solution region, where included points, which are like closed circles, the closed endpoints, they are denoted with square brackets, while excluded points and positive or negative infinity, we'll look at some examples in a minute, they are denoted with round brackets, which I actually call parentheses. So just to make sure we're clear, the square brackets look like this, right? Square. The round parentheses look like this. And I'm just going to add on that IB, which you'll see next year, sometimes uses an additional type of round parentheses, meaning they're not included. And they actually use backwards backwards square brackets. That's a little obscure. I don't know whether I might show that to you as we look at some examples. So I'm supposed to add formal set builder and interval notation, so the two new kinds of notations to describe the solution sets for examples E, F, G, H, I, J, and K above. All right, let's go all the way back to example E. And we'll express it in formal set notation and formal set builder notation and an interval notation. All right, here we go. Let's do formal set notation first. We'll open up the set of braces. We're going to say, all right, we have all of the values x such that, let's look at the number set that x belongs to. I'm not looking at only the integers or only the rational numbers or only the natural numbers. I'm including every single real number in between -4 and 1. So x belongs to the real number set. Are there any other conditions to my values of x? Not only do they belong to the real numbers, but I can see that x is everything in between -4 and 1, where the 1 is included. So this is the part where we can just put in the inequality that we had in an informal set notation previously, and then we'll close our braces. I could also describe this information in interval notation. An interval notation looks a lot like a set of coordinates. My -4 is my beginning endpoint, but it is not included, so I'll use a round bracket. So -4 is the beginning, but not included, comma, and my endpoint is +1, which is included, and that's interval notation. I know it looks like coordinates, but you have to realize that there are different contexts for the notations that you see in mathematics. And in this situation, where we're mixing a parentheses with a bracket, clearly it's not a set of coordinates. It must represent a domain of values ranging from -4, not included, up to 1, included. Let's do part F. To describe this number set, or this solution set, in set builder notation, let's open up our curly braces. We want to describe all numbers x where, once again, we can see that x is an element of the real numbers, because I can include all rationals, all irrationals, all whole numbers, all negative numbers, every possible imaginable number. So all of the real numbers is the number set. And in fact, every time that you shaded a whole bunch of numbers on a number line, a whole region on the number line, you'll find that it's always the real numbers, because it's every number in between the endpoints. And yes, I've got some additional restrictions. I know that x must be less than 0, or, and I can use a comma to mean or, x is greater than or equal to 3, and close the braces. If I wanted to describe this in interval notation, in fact, I've got two different regions that I need to describe. So interval notation becomes a little bit more complicated here. What's the left endpoint of this first region? Well, in fact, the left endpoint goes on forever to negative infinity. And negative infinity isn't a number that you can ever reach, which is why we put a round parentheses around it. So we're going everything from negative infinity, where that number itself could not really be reached, and we're extending all the way to 0, round bracket, because 0 is not included. However, we also want to include another solution set within this solution, so I'm going to say union to describe that there's another interval coming up, and we're going everything, the left end point is 3, which is included, so square bracket, all the way up to positive infinity. And every time you have an infinity, whether it's positive or negative, it must be accompanied by a round parentheses. Let's move on to exercise G. Okay, so to describe this solution set in formal set builder notation, open up my braces. I'm dealing with all values x such that x is a real number, but x is everything in between negative 2, not included, and positive 1 included. So you see that set builder notation is actually fairly similar to the inequalities that you've already been working with. There's just a couple of other details you need to remember. These curly braces, the x, the vertical line, which means such that, so there are some conditions to follow. And then we describe the number set before giving the inequalities that we had already. And in interval notation, we can see that we're going everything from negative 2, not included, up to positive 1 included. Part H. Looking at my final solution set, I can see that I've only got one solution region, which begins from negative infinity. I'm supposed to do it with formal set notation first, aren't I? Sorry. Let's do the formal set building notation. So we'll open up a set of curly braces. I'm dealing with all x such that x is an element of the reals, and x is less than or equal to 3. In interval notation, I have the interval that goes everything from negative infinity, with a round parentheses, because it's an infinity, all the way up to 3, which is included. Anywhere that you put a closed circle, that's going to be a square bracket. Now, I alluded to this earlier, and I don't want to belabor this point, but I'll just sort of mention that another way I could have done this particular interval notation, I could have described this round bracket as a backward square bracket. And I've seen IB do that on some exam papers, so you should at least be aware of that notation. Likewise, down here, we'd have negative infinity not included, all the way up to 3 included. Personally, I'm going to ask you to use the round parentheses notation, but you should be able to recognize the backward square bracket as meaning a round parentheses, not included. Alright, we've still got a couple more to do. I. In formal set builder notation, I've got x such that x is an element of the real numbers, but x is greater than 2. In interval notation, my left-hand endpoint of my solution region is 2, not included, and my right endpoint is positive infinity, which can never be included. J. Look at that, I've included the entire number line. So in set builder notation, I'm dealing with all x such that x is an element of the real numbers, and there's no more conditions. That's set builder notation. Interval notation, my left endpoint is negative infinity, and my right endpoint is positive infinity, neither of which can be included. And lastly, in part K, I've got no solution. This is a very tricky thing to do. In formal set builder notation, we can just give an empty set that looks like this. Or you could describe it as the empty set, which is a 0 with a line through it. And there is no interval notation that you can use. Again, we would just show that there's no solution.